Basic probability laws. We're going to look at some probability laws, sometimes called probability rules, that govern the field of probability and how we can compute the chance of some event occurring from some experiment. So these are rules that are mathematical in nature. We could look at them at a rigorous mathematical level, but for our class, again, we're not going to do that. If you are interested in that sort of thing, you may want to look up Kolmogorov's axioms or the probability axioms. Okay, but starting off, when we think about probability, it makes sense that the probability of some event A, that is the chance that A will occur, is always bigger than or equal to 0, so I'm going to write it that way. That is, 0 is less than or equal to the probability of A, which is less than or equal to 1. It makes sense that the chance of A is bounded between 0 and 1. And mathematically, that's how we're going to think about probability. It's a function that acts on an event, and the output of that function is always between 0 and 1. If the probability of the event is 0, then that event cannot occur. If the probability of the event is 1, then that event must occur. And anything in between 0 and 1 is a measure of our uncertainty regarding that event. Another term here, or a term, mutually exclusive. Events are mutually exclusive if the occurrence of one of the events excludes the possibility of the occurrence of the other event. So here's a Venn diagram of that, a picture. I'm going to draw a little square here that's going to represent the sample space S. Within the square, I'm going to have A, this circle A, another circle B. Now A and B are contained within S, but there's no overlap between A and B. Okay, so we say they're mutually exclusive. The complement of an event A is the event that A does not occur, and it's denoted by A bar. And the Venn diagram for that event, that is the complement of an event, is, again, we're going to start off with a sample space S, have some circle A that represents the event within S, and then A complement is everything outside of A but contained within S. Okay, with these two definitions in mind, give it some thought, but A and A complement are mutually exclusive, right? They don't share any outcomes from the experiment. Okay, a few properties of probabilities here, 3 of them. Suppose A and B are mutually exclusive events. They don't have any outcomes in common. Then P of A and P of B must satisfy the following. Their probabilities need to be between 0 and 1, and that's not surprising. We've kind of already looked at that. The probability of A or B, we say either A or B, is the sum of probability of A and probability of B. And then thirdly here, the probability of A plus the probability of A complement equals 1. And similarly with the event B. But this right here has a special term for us. It's called the complement rule. So the complement rule says if somebody pays you a compliment, you tell them thank you. Well, actually, in probability theory, the complement rule, okay, that wasn't that very funny, but the complement rule in probability theory says that the probability of an event plus the probability of its complement is 1. And if you look at the picture of this Venn diagram here, That makes sense. Okay, if the probability of the sample space is 1, which is very intuitive, the chance that you would see something from your sample space is 1, then the chance of seeing something in A plus the chance of seeing something in A complement should be 1. Okay. The union of two events, so a couple more definitions here, is the set of all outcomes that are included in either A or B or both, just to be clear, and it's denoted with this notation here. A, we say that's A union B. A Venn diagram that represents this, again, we have our square. S is our sample space. A union B, I've drawn A and B as these circles here that have some overlap and some non-overlap. And so the union is everything in A or B or both. So the shaded part is the union of A and B. The intersection of A and B is the set of outcomes that are included in both A and B. So if we looked at the Venn diagram for that, again we have our triangle here, not a triangle, our square, and I have A and B have a little overlap. The overlap set, that is the intersection. The outcomes that are in A and B are in that intersection there. The intersection is always contained within the union. Okay, you can look at the Venn diagrams and see that that is the case. Moving along here, the probability of the union of two events, so playing off of this definition of union of events, is the probability of A union B is the probability of A plus the probability of B minus the probability of A intersect B. And that makes sense. If you look at this Venn diagram here, and just in terms of shading, if that was representing probability, the probability of A union B, you could get to that by adding the shaded area of A and the shaded area of B, but you've double counted the intersection in there, and so we're going to subtract off for it. And that's what this formula does here. It subtracts off the intersection once to contend with that double counting. And this rule right here, just to give it a name, is typically called the addition rule. Okay. So let's look at an example that illustrates some of these ideas. So here's an example. So hit the pause button and read it, but I want to give credit to Dr. Joseph McWilliams. This is from his textbook, from Dr. Joseph McWilliams, a retired statistics and mathematics professor at Stephen F. Austin. Okay, so we have a country club. It has 100 members. 50 are lawyers, 30 are liars, 10 are lying lawyers. I'm going to let A denote the set of lawyers and B denote the set of liars. Okay, so I want to look here at a Venn diagram. So again, I've got my square there that represents S, all people in this country club. There's 100 members in there. Now some are lawyers and some are liars. Okay, I'm going to let A be the set of lawyers and B is the set of liars. Now when I draw B, I'm going to be careful to have some overlap with A because I was told that 10 members are lying lawyers. Okay, so here's a Venn diagram that illustrates this scenario. And from this, I want to write out some information. If what we're told is that 50 are lawyers, and so if I can write this out, N of A, the number of people in A or the number of outcomes in the event A, if you want to think of it like that, is 50. If you want a picture here, or on your picture here, you can draw a 50 to that circle A. The number that are in B, the number of liars, is 30. Okay, so we could draw a 30 to the circle B. Now, what does the 10 represent? Well, there's 10 that are lying lawyers, and so those are in the intersection there. So the number that are in A intersect B is 10. Okay, so that sets up the information we have so far. All right, so with that in mind, suppose that we kind of think of this as an experiment. A member is randomly drawn. What is the chance that we would get a lawyer? So P of A, what is P of A? Well, it would be N of A divided by the number in the sample space. And here I'm playing off of the assumption that our outcomes are equally likely. So N of A, there's 50 over N of S. How many outcomes are in the sample space? Well, there's 100 country club members here, so P of A is 1/2. So if P of A is 1/2, that means P of A complement, if you use the complement rule, is 1 minus P of A. So that would be 1 minus 1/2 there. Okay, you could get A complement directly by knowing there's 50 in A complement and dividing that by 100. In a similar way, P of B, the probability that a person drawn is a liar, is the number that are in B divided by the number that are in S. Okay, number that are in B, there's 30 out of 100 in S. So this is 1/3 there. And so also P of B complement, using the complement rule, would be 1 minus 1/3 or 2/3. Okay. I'm sorry, I got my math all wrong here. That is not 1/3. 0.30. We'll write it that way. I could reduce it to 3/10 if I wanted to. Uh-oh. Okay. 1 minus 0.3 or 0.70 is the probability of B complement. Probability of A intersect B. Well, we know how many are in A intersect B. There's 10 of them, and there's 100 in our sample space. So the probability of A intersect B is 10 out of 100 or 1/10. I think I did my math there right. The probability of A union B. A couple of ways to tackle this. We can use our addition rule, which tells us that the probability of A union B is the sum of P of A and P of B minus P of the intersection. So we've got those pieces, and so let's go with that. P of A plus P of B minus P of A intersect B. That is, we got this already to be 0.5 plus 0.30, then minus 0.10, that's the intersection probability. So we get here 0.70. All right, that's one way to do it. Another way to do it, well, let's look at that. Another way to do it is to look at A union B and partition it. What I mean by that is divide it up into these three pieces. The part of A that does not have B, the intersection, and the part of B that does not have A. Divide it up into those three pieces, add them up, and I should get 70. And if you look here, so let's just make sure that's the case. If 50 are in A and 10 are in A and B, or A intersect B, then there's 40 that are in A but not in B. In a similar way, if 30 are in B and 10 are in A intersect B, then there should be 20 in B but not A. Okay? So 40 plus 10 plus 20 is going to be 70 out of 100. That's another way to get to the intersection the union probability. The probability of A intersect B complement. What is this? If we think about what this is saying here, A is the event that the member is a lawyer, B is the event that the member's a liar, so B complement, the person is not a liar. So this is the probability that you would choose what? An honest lawyer. That's what that is. Okay, so if we look here at our Venn diagram, that should give us some insight into that. We want A intersect B complement. So that's the outcomes in A but not in B. Well, that's going to be the 40 here. In fact, if I want to complete this information a little bit more, I can. The number that are in A but not B is 40. Equivalently, the number that are in A complement or not A but in B is 20. Okay, but here we wanted the probability of a honest lawyer, 40 out of 100, so 0.40. Okay, next question. What does A complement intersect B complement represent? So let's think about our Venn diagram. So A complement is everything outside of A. I can draw a picture for that. Everything outside of A. B complement is everything outside of B. Uh-oh, I should erase that mark there. That one too. Oh, that came from A, didn't it? Or A complement. So the intersection of